The Unit 1 exam will cover topics ranging from scientific notation in the course introduction to all topics sections A to F in Unit 1. Specific concepts to review include scientific notation, periodic motion, relative motion, graphical and mathematical addition and subtraction of vectors, interpreting position time, velocity time, and acceleration time graphs, relationship between displacement, time, velocity, and acceleration, and Newton's 3 laws. Topic 1, scientific notation. In the textbook, you can find information on this on pages 7 and 8, and you can find questions on it in AFL 01. There are two key components to this section, and that is knowing how to transfer your answers into scientific notation on the final exam and on the unit exam. All answers should be given in a scientific notation unless they are anything times 10 to the 0. In other words, they don't need scientific notation. So for example, the number 347.8 meters south. Okay, so that would be a position or displacement. That should be written as 3.478 times 10 to the 2. We know that because if you were to multiply this out, 3.478 times 10 squared, or times 100, you would get 347.8, and that would be meters south. Now on the unit exam, I won't be too sticky with it, but I know on the final exam that they are, so we may as well get used to writing it this way right away. Give you another example here. Maybe I won't erase that. I'll just add a new page. If it's the other way, if you have 0.005 seconds, that would be 5 times 10 to the negative 3 seconds. Okay, now it's not 5.0 or anything because we don't have any zeros trailing the 5. But if it were 0.0630 seconds, then that would be written as 6.30 times 10 to the negative 2 seconds. And the reason we do have a 0 at the end here is because we have a 0 here, which indicates that it's accurate to the 10,000th place, or the 4th decimal place. The second important part from scientific notation and scientific notation and calculations involving measured quantities is significant figures. Making sure that a measured quantity can only be accurate to the degree that your measurement tool will allow. So in other words, a meter stick with millimeter measurements can only be accurate to the nearest half a millimeter. We can accurately look at that and say, well, is it closest to the half millimeter, or which whole millimeter on either side? So for example, And then when you use those measured quantities then to make a calculation, you have to be sure that you're only keeping in your final answer the correct number of significant digits. So let's give an example here quick of an addition and subtraction question. This is, of course, on your in your text on pages 10 to 13. If you're adding up several quantities, 12.6 and 3.45 and 136.248. Okay, if we're adding those together, 8, 9, 12, 12, 5, 152.298. However, the least accurate number is right here, 12.6, and it's accurate to 1 decimal place. So our answer can only be accurate to 1 decimal place. So we would have 152.9 makes it go up 3. That would be our answer. So when you're adding and subtracting, it's whichever is the least accurate that many decimal places. However, when you're multiplying and dividing, it's a little bit different story in that you want to keep the whatever number of significant digits that the least accurate measurement has. So for example, if we're going to multiply 12.7 by, let's say, 3.2, okay, 38.64. Now, it doesn't matter when you're multiplying what decimal places are there, how many decimal places are there. It matters how many significant figures. In this number here, 12.7, there is 3 significant figures. In this one, there's only 2. So our answer can only have 2 significant figures. 1, 2. So our answer would be, rounded up, 39. So although both of the numbers you're multiplying in the question are accurate to the nearest tenth, the answer can only be accurate to the nearest whole in this case because there's only 2 significant digits in here. If we take this exact same question, or very close to the same question, 12.7 times 3.20, we now know that this answer is accurate to 2 decimal places, or 3 significant figures, in this case. Our answer is still going to be the same. What was it? 38.64. However, this one now has 3 sig figs, and this one has 3 sig figs. And because both questions, or both numbers in the question have 3 significant figures, our answer can have 3 significant figures, and therefore the answer would be 38.6. Section 2, periodic motion. In your textbook on pages 17 to 21, and questions can be found in AFL 04. There may be some questions on your exam referring to frequency and period, and how a strobe light or other periodic motion can be used to measure time. An example that you have been using of periodic motion to measure time is the ticker tape timer in your lab experiments that you've been doing. So for some examples here, let's say we have a ticker tape timer with a frequency of 60 hertz. What is the period? In other words, how many seconds are there between each dot on the ticker tape? Well, frequency is equal to 1 over the period, which that means that the period is equal to 1 over the frequency equal to 1 over 60. And if we bring in a calculator, 1 divided by 60, 0.016 repeating. Or 0.017. Section 3, Relative Motion. Information on this section can be found in the introduction of Section A. Remember that relative motion refers to whether or not an object can be considered in motion depends on the reference frame that it's in. The example that we gave in the introduction here was you passing a vehicle on the highway. There is some good information on that on a YouTube video located here. If you type this into your browser URL, or you click on the link, I guess you can't click on the link. You have to, if you open up the SmartBook notebook file, you'll have to copy and paste this into a browser. And that will take you to a video on relative motion, a bit of a review video that I created. Here's a perfect example of a question that may show up on an exam. A race car is moving at 50 meters per second on a straight section of racetrack. A second race car is moving parallel to the first car in the same direction and the same speed. Which of the following is moving relative to the driver in the first car? The driver in the second car. Well, because they're both moving parallel to each other in the same direction at the same speed in a straight line, relative to each other, the drivers aren't moving at all. Neither is the second car. Neither is the first car, of course, because the driver's in it, so the car's not moving relative to the driver. However, the racetrack is moving relative to the driver, or vice versa, the driver is moving relative to the racetrack. It would all depend, again, on your frame of reference. For the driver in the car, it appears that the track is actually moving. However, to an observer standing still on the track, it would appear that the race car and the driver are moving. So in this question, the correct answer would be D, the racetrack. A second important part to this is uniform motion and non-uniform motion, and understanding the difference between the two. You can find that information in the course here, where there is links to some examples of uniform and non-uniform motion, as well as some information from the textbook on pages 45 to 46 on uniform velocity. But the basics here is just to know, if I give you a description of motion, you have to tell me if it's uniform or non-uniform, and you may also have to give me a definition of uniform and non-uniform motion and supplying your own example. Section 4, graphical and mathematical addition and subtraction of vectors. We spent a great deal of time on this. There's a ton of information in videos here already, so I'm not going to do a lot of in terms of review here. In this section I covered quite extensively with videos for each one. You won't likely have to do an example of each type that was given in the course here. However, you'll have to know each type because you never know which type I'll choose for actual questions on the exam. Section 5, interpreting displacement time or position time, velocity time, and acceleration time graphs. It's a large section on this in your textbook from page 47 to 69. Key information that you'll need to know here, though, is how to interpret the graphs. For a position time graph, you're going to need to know what each of these shapes mean. In this case, our displacement is steadily increasing. Therefore, we know that we have a constant velocity. Here it's steadily decreasing, so therefore we know we have a negative constant velocity. Here it's a straight horizontal line, therefore we know it's a constant velocity equal to 0. In this case, we have a curve going up, which we know to be a positive acceleration. Here we have a curve that's slowly bending down, so we know we have a negative acceleration. We don't know if these are constant or not. They look relatively constant, but very difficult to tell that from a position time graph. You would need a velocity time graph in order to tell for sure. So here we've got some velocity time graphs. Here the velocity time graph is steadily decreasing, therefore we know we have a constant or a negative constant acceleration because the slope is negative. It's moving down from left to right. Here it's moving up from left to right in a straight line, so we know we have a positive constant acceleration. Here it's curved up, so we know we have a positive increasing acceleration because the slope of the line is constantly increasing. The slope of a tangent line to this is constantly increasing and therefore we know we have an increase in acceleration. And here the velocity is constant, therefore we know we have a constant acceleration equal to 0. Or in other words, there is no acceleration. One of the things you'll be sure to need to do on the unit exam is to take a velocity time graph like this and transfer that into both a displacement or position time graph and an acceleration time graph. So to move from velocity time to position time, we need to find the area beneath. All right, got that set up a little better. Now let's see if we can transfer that. So to find the dt graph, what we need to do is find the area under the curve. So from 0 to 2 seconds, the area beneath this would be half the base times the height. So half of 2, which is 1, times the height of 3, which is 3. So we know that at 2 seconds, the position is 3. Then for the next 2 seconds, the position increases another 1, 2, 3, 4, 5, 6 from here. So that would put us to 9. Oh boy, my scale doesn't work. Let's change that scale so that it goes 3, 6, 9, 12, 15. How about that? Okay. So in that case, that doesn't go there. So at 2 seconds, it's 3. Okay. Then in the next 2 seconds, it goes up another 6 blocks. So it goes up to 9 in the next 2 seconds. So by 4 seconds, we're up to 9. Then at in the next 3 seconds, I guess it would be from 7 seconds to 7 seconds. Okay, well let's break it here instead. Okay, let's break it right there at 5.5. So for the first second and a half, it's still increasing because we still have a positive velocity, right? Positive velocity, this would be, oh boy, what would this equal? 1.5 times half of, it would be 1/2 of 1.5 is the base times the height of 3. That would be 4.5 divided by 2, 2.25, 2.25. Okay, so we're going to go up another 2.25 from 9. So right about there or so. And then we start going down again. And this time we drop back down another 2.25, so we're back down here by the time we hit 7 seconds. Then from 7 to 9 seconds, and the reason we go down is because now our velocity is in the negative direction, right? We're backing up. So if we're backing up here, we're moving forwards, 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 forwards. All of a sudden at this point right here, 5.5 seconds, we reverse our direction. Come to a complete stop, reverse our direction, and start going backwards again. And from 7 to 9, we go backwards 6. So we go back down to here. And at that point, we're still in negative though, right? Our velocity is still negative, so we're still backing up. We're just not backing up as fast. We're starting to slow down our reverse. And this is going to be, what did we say it was? This is going to be Half the base is 1 times the height. The base is 2, which is 1. So half the base is 1 times the height of 3 is 3. So we're going to have to go backwards another 3 by the time we hit 11 seconds, so right there. Now, to draw this in here, we know that from in section B here, we have a constant velocity. If it's a constant velocity, then we know we have a straight line, right? So we can draw our best straight line there. However, in here, the velocity is increasing, right? For the first 2 seconds. So we know that this needs to be a curved line. Then we have a straight line. Now here again, we have a negative acceleration. So it's going to be a line that curves down. Then here again, we have a constant velocity. So a straight line. And then here it starts slowing down, so we curve like that. There we go. That's your position time graph. Now we need to transfer it into an acceleration time graph. All right, let me change it to now an acceleration time graph. I may need to change my scale here again. We'll find out fairly quickly here. All right, acceleration is merely a measurement of the slope of the line. So in this case, slope, rise over run, 3 divided by 2, 1.5. So for section A, up to 2 seconds, we have a constant acceleration. We know it's constant because the velocity time graph is a straight line. Constant acceleration of 1.5. Then for section B, we don't have any acceleration. The velocity is constant, so our acceleration is 0. Then in section C, we have a negative acceleration. The slope, rise over run, the rise is 1, 2, 3, 4, 5, 6 in the negative direction, so negative 6 divided by 1, 2, 3. Negative 6 divided by 3 is a negative 2. So in this section we have a negative 2 acceleration up to 7 seconds. Just fix that up a little bit. Okay, close enough. And then we know that for section D, again, acceleration is 0 because it's a horizontal line. So from 7 to 9 seconds, 0 acceleration. And now we have rise over run. Our rise is 1, 2, 3 in the positive direction. Divided by 2. Again, we have a positive acceleration of 1.5. And that would be your AT graph. Section 6, relationships between displacement, time, velocity, and acceleration. This, again, many of the equations for this come from pages 45 on. Equations such as velocity equals distance over time. So velocity equals change in displacement over change in time. and any derivative equations of that, including velocity average, or average velocity, over a period is equal to the change in displacement over the change in time. Instantaneous velocity would be the limit as change in as delta t goes to 0 of delta d over delta t. However, you don't actually have to use that equation. What you do have to know from that is how to calculate the instantaneous velocity, or rather not calculate, but estimate it from a graph by drawing a tangent line to the graph. So if we have a if we have a d versus t graph that goes something like that, you need to know that to calculate our instantaneous velocity right here, we draw a tangent to the curve at that line and calculate the rise over run, or the delta d over delta t of the tangent, and that gives us our instantaneous velocity at this point there. Same thing if we wanted to calculate it here, we would draw a tangent and we would calculate the delta d over delta t. Another equation you need to know from there is that the acceleration is equal to change in velocity over change in time. And derivatives of that, one of those being v2 minus v1, those both being vectors, of course, divided by t2 minus t1. Of course, average acceleration and instantaneous acceleration are determined the same way as they are for velocity. Average is just, again, delta v over delta t for the total portion that you're looking at. And instantaneous acceleration, add another page here. If we have a v versus t graph that goes something like that, and we want to calculate what the acceleration is at that point, we draw the tangent, calculate the delta v over delta t for the tangent, and that gives us our instantaneous acceleration at t whatever t is equal to there, if it's 5 seconds or 4.5 or whatever it is. And of course, the very useful equations on page 69 and 70, you need to know how to use those equations. Please ensure you know how to use those equations. That are all derived from the two equations we just talked about. Those two equations being velocity equals delta d over delta t, and acceleration equals delta v over delta t. Knowing that, using those two variables, those four variables, acceleration, velocity, displacement, and time, we can work all kinds of problems that involve velocity, displacement, time, and acceleration. Be sure you know those equations. Section 7, the last section, Newton's 3 laws. These can be found on pages 130 to 149. It's important that you are able to state the 3 laws of motion, and that you have a good understanding of what each means. The first law, Newton's law of inertia, basically means that any body in motion, any object that's in motion, will stay in motion. Any object at rest will stay at rest unless it's acted on by an outside force. So if we were out in outer space and there was no gravitational pull, there was no other objects anywhere in the universe, and we were traveling along at 10 meters per second in a straight line, we would continue moving at 10 meters per second in a straight line forever. Of course, there are other things out there causing gravitational force, like planets, suns, galaxies, the whole bit, and so that's why nothing actually does continue in a straight line, an exact straight line. However, there are good approximations of it in real life. Newton's second law basically says that when you apply a force to an object, an unbalanced force to an object, it begins to accelerate, begins to speed up. That acceleration is in the same direction as the force that is being applied. That makes sense, right? You see a ball, you give it a push, that ball starts to speed up in the direction you're pushing it. As soon as you let go of the ball, though, you are no longer applying force to it, and therefore it keeps rolling in the same direction unless friction with the ground causes it to slow down. The other part of Newton's second law is that the acceleration is directly proportional. That's what this symbol means. Directly proportional to the force applied to it. And pardon me, force, I should know better, is represented by a capital F. So it's not confused with frequency. And these are vectors because when the force is applied in a certain direction, the acceleration is also in that same direction. The other thing that Newton's second law says is that acceleration is inversely proportional to the mass of the object. In other words, the heavier the object, the less acceleration there is, right? If you put a bigger number on the bottom here, 1 over it is going to be a very small number, so acceleration is a very small number. The equation we get from that is that force is equal to the mass of the object times its acceleration. There are, of course, derivative equations of that, such as acceleration is equal to force divided by the mass. So if you apply a certain force, you know the magnitude of that and direction of that force, divide it by the mass, which is a scalar number, you're going to end up with the acceleration, a vector pointing in the same direction as the force. And of course, that the mass is equal to the force divided by the acceleration. going back to our talk about the vectors, if I can find that, that is graphical and mathematical addition and subtraction of vectors that I talked about being very well covered in section B using videos. You can watch those again if you need to review it. We need to be aware that Newton's second law has a vector nature and that you will have questions applying to that. What that basically means, that by the way is page 141, section 4.5 in your textbook. What that means is that if you apply a force, let's say we've got a box here, and you've got a rope tied to the box, and you have your hand on that rope, and you're pulling with a force in that direction of 10 newtons. And that direction is, say, 30 degrees to the horizontal. What is the horizontal component of that force? Well, we know how to do that because that is covered in resolving vectors. Here it is, resolving vectors graphically into components, resolving vectors mathematically into components. You will for the most part, just be doing the mathematically when you're working with Newton's second law. I won't have you do it graphically. Now, knowing this though, we need to use the Sakatoa rule, right? Sorry. So Toa. Okay, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tan is opposite over adjacent. So, given this, we have a vector pointing that way. That is 10 newtons. We have a 30-degree angle. We want to know what the horizontal component is. Well, we know that sine 30 equals, oh, pardon me. That wouldn't be the right one to use if we want to find the horizontal. We want to find the horizontal, we need to use cosine because we want to find the adjacent. So cosine 30 degrees equals the adjacent over the hypotenuse, or x over 10 newtons. Therefore, x equals 10 newtons times cos 30 degrees and I should probably know this off by heart, but I don't. Cos of 30 is 0.866. Double check that. Yep, 0.866. Multiply that by our 10 newtons, and we find that it's 8.666. And because our 30 degrees, we'll assume that's the two significant figures. Our 10 newtons, we'll say that's the 10, or to two significant figures. Our answer should be the 2, so we would have 8.7 newtons. X equals 8.7 newtons. So that is the whole idea of the vector nature of Newton's second law. You will need to make calculations for questions on the exam relating to that as well. The third law of Newton's laws of motion is that for every action, there's an equal and opposite reaction. In other words, if we have two boxes connected by strings, and here's your hand. This time you're just going to pull, it's not a very good hand, but you're just going to pull straight sideways, okay? And this box weighs 2 kilograms, and this box weighs 1 kilogram. And let's assume that they're on a frictionless surface here. Impossible in real life, but easy to approximate if, say, we are on ice. And you're pulling this frictionless surface, so the only force is the 10 newtons you're applying to the string here. All right, you're pulling with 10 newtons in this direction on this box. Or rather, you're actually pulling on the string. The string is pulling back with 10 newtons of force on your hand. The string is also pulling forwards on the box with 10 newtons of force, and the box is pulling back with 10 newtons of force on the string. And here's where it gets interesting. Let's call this string 1 and this string 2, and this box 1 and box 2, okay? What is the acceleration of the entire unit here when you start pulling on it? Remember, frictionless surface, so we have no drag. Therefore, we know that acceleration is equal to the force divided by the mass is equal to 10 newtons divided by a total of 3 kilograms equals 3.3, let's go 3.4 to two significant figures. 3.4 meters per second squared. Knowing the acceleration of the total unit, we can find out that, let's just grab our drawing here. Paste it into a new page. Knowing the acceleration equals 3.4 meters per second squared, then we know the acceleration of our second block. So acceleration B2 is also 3.4 meters per second squared, because that can't change. It's all connected. Well, if we know that the acceleration and we know the mass, then we can find out what force string 2 is exerting on box 2. So force equals mass times acceleration equals 2 kilograms times 3.4 meters per second squared equals 6.8 newtons. So string 2 has a tension of 6.8 newtons. String 1 has a tension of 10 newtons. So we know string 1 has to be stronger than string 2. Or I guess what we could say is string 2 only needs to withstand 6.8 newtons, or to be on the safe side, 7 newtons. However, if you use this, if you use if you use string for string 2 that can withhold 7 newtons of force, but anything more than that it snaps, you're fine. If you use that same string here, it's going to snap. That concludes the review for exam on Unit 1.